Should get a notification. Okay. Welcome, Steve.
So the first thing I'm going to do is apologize. So I just set up a new ultra wide monitor, so I can't share a whole screen anymore, or else it's going to look all weird. So I'm going to be popping between different windows and with my screen share throughout the presentation. So so first off, hi everyone. My name is Steve Lorello, and I'll be presenting to you a brief introduction in computer vision using .NET. So a little background about me: I'm the .NET developer advocate at Vonage. So now, of all the topics in computing, computer vision is actually probably my favorite. With it, you get to take a set of fairly abstract mathematical concepts and apply them to something that's really quite powerful and useful. Now, if you're anything like me and you've dabbled in raw computer vision techniques before, you probably mostly use either Python or C++. Both of which are boundlessly useful for sure, but they can be a little bit limiting in what they allow you to do with your client-side applications. And that's why I'm really excited to kind of explore this with y'all with .NET. So a good place to start is by asking a really fundamental question. What is computer vision? And to answer that question, I'm going to borrow a quote that my computer vision professor in grad school borrowed from a CV researcher. The goal of computer vision is to write computer programs that interpret images. Now, there's two concepts that we need to unpack here. First, what are we interpreting? And then also, maybe a little bit more fundamental to our study here is, what's a digital image? So here's a bit of an agenda of what we're going to be covering today. First, we're going to be tackling that existential question. What's a digital image? Then we're going to be looking at a little bit of hello world code using OpenCV and .NET. And then we're going to start diving into that interpreting part of our definition more. We'll be looking at convolution and edge detection. Next, we'll look at facial detection. And then we're going to actually explore doing real-time face detection on videos. We're going to be using my company's video API for that. And finally, we'll be doing some feature tracking and just a little bit of baseline image projection. So for our first question, what's an image? So here's an image of my muse for this presentation, my dog Zero. You might want to get used to him. You're going to be seeing just a little bit of him throughout this presentation. So what is an image? So an image at its most basic form is a function. That function denotes quantized samples of intensity by position in the two-dimensional grid. Those intensity values you might have heard referred to as light pixels, denote light intensity along arbitrary ranges. For example, the range of a byte, 0 to 255. Now, there's no rule that says they have to fall in that range, 0 to 255. It's just a convention. And oftentimes when you're talking about grayscale images, they can actually be on the range of -1 to 1 or 0 to 1. But technically, as long as those values lie along a bounded range, the math is still going to hold. And actually, when you get into other applications of image processing, for example, HDR, which literally stands for high dynamic range, that range of values is exponentially larger and technically infinite. So the image of 0 that we just saw, my dog, is a matrix, when you think about it, of size n by m by 3, where n is the height of the image, m is the width, and 3 is the number of channels. And a channel, by our definition here, is just an intensity of a particular color. In this instance, we're talking about red, green, and blue. So this picture here of a pepper is actually a classic example of looking at an image, particularly as an image in a one-dimensional space. So you see this red line drawn through here? Well, that line is actually its own image when you think about it. Now we're using grayscale here because grayscale makes things a lot easier to think about, but the math actually abstracts out to multiple channels, like red, green, blue is the classic example. So like I said, this line right here you could think of as its own one-dimensional image. And that one-dimensional image is denoted by intensity values in this graph here on the right, with the darker spots being lower intensity, so they're lower down here, the lighter spots having higher intensity. Now this insight becomes really powerful, and we'll see later how it's applied. But I really want you to think very briefly about where the edges are in this image. Are they in the peaks? Are they in the valleys? Or are they somewhere in between? So next we'll actually be looking at the crux of this talk, which is using computer vision in .NET. So I'm going to actually be using a tool called OpenCV, which stands for Open Source Computer Vision Library. And as the name suggests, it's an open source tool. It's pretty widely adopted. And while there are other things that do this, essentially the same thing that OpenCV does, MATLAB, for example, has a lot of image processing, so does Octave. I like CV because for the most part, it's free. It's integrated into a lot of different programming languages. And the docs I like because they're, to my mind at least, they're pretty user-friendly. As a bonus to showing you how to do things, they also explain the insights and some of the math behind what each function does. So MGUCV is the .NET OpenCV wrapper that we're going to be using. It's widely available for the .NET framework and does enable you to do quite a lot. And there is, for the most part, a one-to-one mapping between OpenCV and MGUCV. So most things that you can do with OpenCV, you can also accomplish with MGU. I'll also note that if you're like me, you've probably used, and you've used the Python OpenCV library, you might need a little bit of time to adjust the MGUCV as it's a lot truer to the original C++ implementation of OpenCV. And just note that MGU does use a dual open source commercial license. So to actually use OpenCV, so just for our contrived example here, we're going to create a new project. For now, we're just going to create a basic .NET Core console app in Visual Studio. Then we're going to install the MGUCV runtime package with our package manager. And that's mgu.cv.runtime. Your platform. So I'm on a Windows machine, so Windows, for example. And now we're just going to add a little bit of code here. So MGU is structured around a bunch of static functions in the class CV invoke. And here we're going to use 3 of them. I've stored an image under my resources directory called 0.jpg, and that file is just going to be copied down to the build directory. So when it runs, we're just going to assume it's there. So this first line here reads the image of 0 into a matrix. As you're doing that, there's 2 things you really want to note. First, the matrices that we're pulling in here are in the BGR space, which refers to blue, green, red, rather than the RGB space that you might be used to, which stands for red, green, blue. So it's just a slightly different ordering of the channels. All of the structures that we're using in MGUCV, they all implement the iDisposable pattern. So if you want to limit the scope which the memory is being used, you just use using statement or explicitly call dispose and everything. So the second line here actually creates a window with a title provided by the first argument, 0, and draws the image of 0 from the second argument into that window. And the final key, the final line here is wait key, which is similar to a console input. It just waits for you to press a key while you're focused on the image window. Without calling that, the image will disappear immediately and you won't get to see it. So hold on, let me unshare this. And I am going to share my whole screen for a moment. So I apologize if it's going to be a little funky. No. Show image. So here's that program that we were just referring to. So I hit show image. Boots up. And we see 0. It's pretty simple. I mean, just like I said, a contrived example, but just a very basic example of how to use MGUCV. Hold on, let me.
Looks easy.
Yeah, I mean, it's not too bad. So now, here's the output of that program again. So now we're going to move on to the next topic that we're going to cover, which is convolution. Now, convolution is the process of combining two functions to produce a third. So when we're working with images, this generally means taking a large matrix, an image, and running a small matrix, a filter or a kernel, over it to produce a third matrix called the feature image, which is actually what's going to provide us with a lot of our insights. So this is essentially what's happening here. Notice the shaded region in the image is the same size as the filter that's being run over it. That's because this 3x3 submatrix is being dotted against this to produce this dot product in the feature image. So if we run this filter over all the pixels in the image, start up here, run down like this, you would actually produce a full feature image. And typically when we're done with our convolution, we'll actually take the filter or kernel and sum it, and then divide the feature image by the sum of that kernel to normalize it. So to illustrate why convolution is such a powerful tool when we're talking about computer vision, we can really do some really neat things with it. And to accomplish those, the only thing we need to do is adjust our kernel. So this kernel right here is called a Sobel operator. So the Sobel operator enables you to do something really critical, edge detection. So do you remember that image of a pepper that we looked at earlier? And I asked you to think about where the edges are. Are they in the peaks or the valleys, or are they in between? Well, the correct answer is actually in between. So if you at some point took or can recall from school calculus, you might remember something called a derivative. And a derivative is just the rate of change between 2 points in a function. It's your slope at an instantaneous point. And it's the derivatives that the Sobel operator is going to calculate for each image in the pixel. And remember how I said convolution is combining two functions or images to produce a third? Well, that's exactly what we're doing here. We're combining our input image and our kernel function to produce a third function or image. An image showing the magnitudes of the derivatives, also known as the gradients, and maybe more clearly referred to as the edges of the image. So these are two commonly used Sobel operators. The first is going to work on all the gradients in X, and the second is going to work on all the gradients in Y. And after combining the two, you get a third image, the full gradient image. So here he is again, my buddy Zero, in his Mr. Rogers sweater, as I like to call it. Notice all the edges of the image. So when you think about it, those edges, the places where the color is changing really rapidly, is really where we're getting most of the information of the image. The flat surfaces, the parts where the color's not changing particularly much, they don't really tell us that much about what's going on in the image. So after running convolution with a Sobel operator over our image of 0, we're left with a gradient outline of the edges of the image. Those are the parts that are very bright in this output image. Now that operation of convolution has a wide array of applications, particularly when it comes to feature detection. And we can actually leverage that in something else that you might have heard of, convolutional neural network, which is a topic for a different day. I'm not going to get into that today, but some neat background about what convolution really leads to with image processing. So if you want to calculate the Sobel gradients for an image, this is the process. So I'm assuming that all the images that I'm reading in are grayscale images, or not grayscale, are color images. And so the first thing we need to do is actually convert our color images to grayscale. So that's what we're doing in this first line. So I've already pulled in the image. I've constructed these matrix objects, which are the gray, grad X, grad Y, abs grad X, abs grad Y, and Sobel grad. Those are just like matrices. They're newed up like any other object you've ever used. They don't require any arguments to create. But what this first line is doing, CVT color, it actually converts the images between the different color domains. So in this case, we need to go from the blue, green, red domain that OpenCV reads the images and the color images into, and we need to convert it to gray. So the next line is doing something that you'll see kind of a lot of. when you're looking at image processing, it's doing a Gaussian blur. And I'll explain what that does next, but it's actually blurring the image, which is a good thing in our view here. So the next thing we need to do is we actually need to calculate the gradients in X and the gradients in Y separately. So that's this right here, the CV invoke.sobel. So the arguments here are the gray image that we're going to store things into, or the gray image that we're getting our data from, I apologize. The gradient image that we're going to store them into, a depth type. Depth in this case is the number type that we're using. Now, we're using a unsigned short here, which is different than the gray type. So the gray type is a unsigned byte. So an unsigned, what is it? Yeah, unsigned byte, I apologize. Just an 8-bit integer, or 8-bit unsigned integer. And we need to store them into these 16-bit unsigned integers. And the reason we need to do that, if we go back a little ways and we look at our calculation here, the dot product that we're producing could overflow very easily the 255 maximum of our, of our unsigned integers, or unsigned 8-bit integers. So we need to actually convert it to the signed integers temporarily. This next argument here is the X factor that we're using. This argument's the Y factor, and this last argument is the kernel size. So if we're doing X, we do 1 for the X factor, 0 for the Y factor, 3 for the size. For Y, we do 0 for the X factor, 1 for the Y factor, 3 for the gradient size again. And now that we've calculated those gradients, we need to scale them back into that same 8-bit unsigned integer space, which is.
So I have a question. So the Sobel matrices you showed before, with the -2 to +2.
Yep.
Like how do those parameters relate to what's in this matrix?
Yeah. So like you run this submatrix. So like you would replace this filter kernel over here with one of these. So one of the Sobel operators.
Right.
And then you would go through successively, and you would pick out this neighborhood right here.
Right.
And you would dot this neighborhood by that Sobel operator.
Right.
And you would produce your final feature.
Okay.
And the way that these filters are arranged, it actually allows you to highlight the edges in your image.
Right. So I mean, is the Sobel operator always these values?
Yeah. So there's I think there's 4 or 5 different commonly used edge detection operators. Sobel uses, this is a classic example where it uses -1, -2, -1.
Okay. Are you specifying that particular one to use in your call?
Yeah. Because this Sobel right here.
Yeah.
This is actually using that operator. So it's actually using that.
Okay. So it'd be some other kind of Sobel if it was a different filter.
Well, I think the other ones are like Pruitt. I think there's a Howard operator or something.
Okay.
Like that.
Okay. I got it. They'd be called something different.
Yeah. And you can actually, there's actually a convolution function in OpenCV where you can just create your own matrix and use whatever matrix you want. And yeah, you can use a Sobel operator. If you want to scale it up, you can do that too. But yeah, the classic example just uses CV invokes Sobel. Does that make sense?
And then the parameters here, the 1, 0 is just selecting the X or the Y axis.
Yeah. Yeah,
and
exactly.
The 3 is the size of the matrix.
Yeah, so it's the size of this thing.
Yeah, okay, very good. Okay, just want to make sure I understood it.
Yeah, no, that's all good. I've tried using 1, 1 before because I figured that it's just going to do both at the same time. And
right.
It doesn't work. So you need to do 1, 0, 0.
It has to sequence it. Yeah.
So anyway, so you take that gradient image that you produce, and you have to scale it back into the 8-bit unsigned integer space, and then to produce the final output, you add the weighted absolute gradient of X, absolute gradient Y. So you take like half of the values from this matrix, half of the values from this matrix, and you add them together and you produce the final result. Does that make sense?
Barely.
Barely?
I mean, I understand the operations. I'm trying to envision it and what it's doing on an image. Yeah.
Gotcha. So here's actually what it's doing on the image. So this first one here, where we see the vertical lines kind of nicely highlighted, is the gradient in X.
Ah,
And the second one here, where the horizontal lines are highlighted, is the gradient in Y. And you might actually be scratching your head a bit because, wait, X is the horizontal and Y is the vertical. So why is X showing vertical and Y horizontal? And the reason is because the operator that we're using actually calculates the gradients perpendicular to the gradient of the image. So X logically would calculate the vertical lines, where Y would logically calculate the horizontal lines. Does that make sense?
I see it. Yeah.
And so then you take these two, and like with this last bit right here, this add weighted down here, you take them and you combine them, and you produce this final output image, this gradient, and this is the final gradient image. And that actually has both the X and Y kind of X and Y gradients combined to like one final image.
Cool.
Let me pop back out and use and show you this program running. I apologize again. I'm going to have to share my screen with this weird aspect ratio.
What size monitor do you have?
49-inch monitor.
Ah,
And it is absolutely wonderful for productivity work, but I think I need to figure out OBS or something for for screen shares because it just doesn't work. So basic Sobel. So here's that same operation I just showed you right here.
it's a little bit small. It's hard to see. Obviously.
Oh goodness. Let me see if I can zoom in a little bit.
Yeah, it's a little bit better.
Does it make it better?
Yeah.
So that's the same bit of code I just showed you. Here's all the things I needed to initialize first. Just a bunch of newing. Just a lot of newing up here. And then I just show them all. And I also do an mWrite is you write it to a file, basically. So if I run this, it's going to process a bunch of images. So this is the grayscale image.
Mm-hmm.
And then this is the gradient in Y and gradient in X it produces. And then it combines the two of them to produce the Sobel operator. Or not the Sobel operator, the final Sobel output. So that's like, as you
Combined.
can see, yeah, that's the combined functions. And hold on, let me pop back out to my slides. And that really is like, with virtually none of the information from the original image, you have none of the color, you have none of you just have some very basic outlines. You get you get the gist of what's going on in the image.
Yeah, yeah.
Back online here. But yeah, like I said, it gives you a pretty good idea of what's going on in the image just from that.
Mm-hmm.
So now, probably the most ubiquitous kernel that's used is the Gaussian kernel. Now, lots of operations will run what's called a Gaussian blur over the image prior to using it in other CV functions. For example, the Sobel operator that we just looked at ran the Gaussian blur. Now, Gaussian might sound familiar to you if you've taken statistics. It's just another way of saying, it's a fancy way of saying a normal distribution or a bell-shaped curve. We start with some center pixel down here, and we construct our gradient with the further we get away from our center pixel, the lower we weight the individual pixel. The same thing as with our bell-shaped curve here. Now, this value will actually scale up or down depending on the size of the filter. And now, one of the things that really confused me when I first started learning about computer vision was why blurring was so useful. And the reason it's so useful is actually because digital camera sensors tend to actually add a lot of noise to an image. And even a little bit of noise can really throw off a lot of these techniques. And blurring digital images, which actually makes it less detailed to our eyes, removes a lot of this noise and allows our programs to interpret these images better. So to illustrate this point, I think it's helpful to look at an example. So now that's that same image of a pecker that we looked at earlier, and of course an image of Einstein. And both of these images have some artificially added noise. Now, this artificially added noise is really obvious to our eyes, whereas noise that's straight off of a film or a sensor, they might not be immediately obvious, but they are there. And now think about how our edge detector is going to work with these two images. Really poorly, you'd think, right? While the detail is definitely perceivable to our eyes, the oscillation in value between the pixels is just too extreme for a program to gain any meaningful insight of what's where the edges in the image are. Another filter that's really useful and produces a pretty neat result is a sharpening filter. So sharpening filters, whereas this is pulling in like these weights at like a reduced but still a positive value, the sharpening filter actually subtracts the external values away and really magnifies the actual pixel itself. So you create a sharper image. And you can actually, instead of using a sharpening kernel like this, you can also use a the blurred image that you took. You can subtract that blurred image from your original image to get a detail image, and then you can actually magnify that to produce like a sharpening set of detail that you can add back to your original image. So this, for example, is some sharpening code. We take our image as 0, we run a Gaussian blur on it, just like we saw in the last bit of code that we looked at. We can actually create an image from the detail of that image. So you could take 0, which is the original image. You could subtract this blurred image, which leaves just the detail, and then you can magnify that. So for example, here I multiply it by 2 to enhance the detail of the image, and then I add back the detail to the original image of 0. Now see here, we're going from our original image to our blurred image. Now remember, blurring loses detail to our eyes, but it gains clarity for our programs because it removes noise. Now here, we've taken that original image and subtracted the blurred image from it, and what we're left with is the detail. And then we can magnify that by multiplying it, which produces a detailed image that we can now add back to our original image to produce this sharpened image. It's actually probably easier if you look at apples to apples. So see here again, we have the original image of 0 versus the sharpened image of 0. You can see the differences in sharpness here. You could tune the degree to which you're multiplying the detail to increase sharpness, but if you overdo it, you'll actually wash out the image and add a lot of weird artifacts to it. So here is an example with 10x detail added. You'll see that it's actually washing out like large portions of the image, and you're getting these weird pixel values.
I think I can see his heart.
You think you can see his heart? It's possible. He's a skinny guy, so like, but yeah. So now I want to move on to something else that's really cool that you can use computer vision for. And using OpenCV, we can actually run, and that's face detection. And using OpenCV, we can actually run face detection, and we can run it in real time on multiple video streams. So we're going to discuss a technique for facial detection developed by Paul Viola and Michael Jones, which is both really robust and really fast. So we're going to be taking these little masks called heart-like features, which we're going to see in a minute are just very simple little shapes. And with them and an integral image generated from our input image, we're going to determine the relative shading of different regions of the image. And after combining a lot of these heart-like features together, we can build what's called a cascading classifier to perform face detection. So
this isn't limited to face detection. It's any kind of feature detection.
Yeah. So like so this is a classic example for face detection. But if you wanted to do like any other type of feature too, you can build a model for it. Like for example, the classics here. There's a face detector which detects a face. There's profile face detector which detects the side of a face, and there's like eye detectors which detect your eyes. And you can actually combine all these different classifiers together to actually like detect different features. But yeah, it can be used for many different features. And there's actually something called a template match too, which you can take an image and like use that as a template and actually detect that in different places in an image too. And I actually didn't do that. It's something I've considered adding to this presentation, which maybe I will at some point in the future. But anyway, these Harlake features, as they're called, are just simple black and white images. They're split into 2, 3, or 4 different rectangles. And they might look like silly little shapes, but they're actually extremely useful tools to run all kinds of different detection algorithms. Like you said, it can be generalized out to different detection algorithms. But in particular, here we're going to be looking at facial detection. So 1 or 2 of them by themselves aren't really that useful for any kind of image recognition or feature detection, but hundreds of them applied at varying scales to the same image against a well-tuned model could produce really robust and, more importantly, really fast, and I mean can run in real-time video with low overhead fast result. So you're probably asking yourself, you're running hundreds or thousands of these features at the same time, and you have to sum up and subtract all the pixels under each region at varying scales. Now, how could this possibly work performantly? And the answer is actually at the core of the Viola-Jones algorithm, the method that they pioneered. And that's the integral image. And we thought we were done with our calc terms. So if you ever took calculus and recall what an integral is, it's just the area under a curve. It's just the magnitude up to that point in a function. And that's exactly what these are. So these images, they represent the sum of all the pixels above and to the left of each pixel in the image. And what does this do for us, you might ask? Well, the Harlake features we looked at before, they require us to sum the white area and to sum the black area and to find the differences between those two areas. And that produces a relative shading between those areas. And each summation is on the order of n by m, or n is the height and m is the width. And this might be acceptable for one feature, but if the algorithm requires you to run lots of these to robustly detect faces, it's just going to fall apart. So this diagram actually illustrates how the integral image makes this algorithm so much faster. So to find this red rectangle, which you could think of as one of the as representing one of our Harlake features, we only need to take the bottom right-hand corner, that bottom right-hand pixel, subtract the bottom left-hand pixel and the top right-hand pixel from it, and then add back the top left-hand pixel. And that's it. So remember, this image, we've summed the whole thing up. So we summed everything up to this point, we summed everything up to this point, everything above and to the left. So subtracting C away from D removes effectively everything to the left of this rectangle. Subtracting B away effectively subtracts everything above the rectangle, and then adding A back actually adds back the double negated region in this top left-hand portion right here. So with this, we can actually really quickly calculate the shading of the regions covered by our Harlake features. And that, used with some other machine learning techniques, can build we can correlate them all together to build a classifier that will really swiftly and robustly detect faces in an image. So how does this apply to our .NET program? Well, it's actually quite a bit easier than what I just described. OpenCV actually has a large collection of Harlake features prearranged into a model for a cascading classifier. That model is available in an XML file that can easily be ingested using MUCV. So with that model ingested, we just need to construct a cascading classifier, and then it's easy as running a detect multiscale method and then drawing the rectangles on the detected faces. And here it is. All you need to do to detect a face in .NET. You build a classifier. So we create our face classifier. We new up a cascade classifier with our har cascade frontal face default.xml. That's that thing I got from OpenCV. We read in our image, and then we run this detect multiscale. And I set a min size of 300 by 300. And then for each face in there, we use CB invoke rectangle, which draws the rectangle on the image. So here's the result of running that on an image of me. As you can see, it detected my face. So remember how I said I'll tell you in a second why I use this this small size. So that minimum size. So this algorithm is invariant to scale, and it's invariant to scale at such an extent that bobblehead of Roger Clemens that my grandfather got at a Yankee game in like 2001, it was picking up Roger Clemens' face in that thing. So it could actually detect like even face-like features on tiny objects in a room. So that's why I use that minimum size. So this algorithm, like I said, is invariant to scale, but it's not invariant to rotation, and it's not invariant to light changes. So the photometry of like half of my face became like very dark and the other half was very light, or vice versa. The whole thing could just fall apart because that relative shading would be missing. So one other thing to note is this is not for facial recognition. This is for facial detection. There are other techniques that are much more suited to facial recognition, like convolutional neural networks, which I mentioned earlier. So now we're going to use the same technique, but we're going to apply it in a real-time application just to see how powerful it is. And since Vonage pays the bills for me, I'm going to use the Vonage Video API. So I just created a WPF client application, and I add the OpenTalk.client SDK to it. The OpenTalk client SDK is the client-side SDK that Vonage publishes that runs on Windows machines. I'm going to add this iVideo renderer class, or this iVideo renderer face detection video renderer. It's going to implement the iVideo renderer, which is a Vonage class, and it's going to be extended control, which is a WPF class. I'm going to add one of these face detection video renderers to our main XAML file, and we're going to put that in the bottom right-hand corner of the screen. It's going to be called Publisher Video. Publisher is the video stream that's coming from your device going out. I'm also going to add a detect faces and a connect button. The detect faces button is going to help us. It's going to toggle the detection on and off, and the connect button is going to actually connect us to a session. So now that we have the main Windows, I have the main window set up in the main XAML CS file, I'm going to be constructing a publisher object and a session object. Both of those are from the OpenTalk client SDK. Now, ahead of time, I've created an API. I've gotten my API key, session ID, and token. I just hard-coded those for the sake of simplicity, but the API key is part of my Vonage Video API account and project, and the session ID and the session ID and the JWT that serves as the token generated by a server SDK that we publish. They can be built off of just our REST API. I just want to use that. But I'm just hard coding them in here because I didn't want to stand up a server for this. So notice how I'm constructing the publisher here. I'm passing in that publisher video element that I referred to back here, and that's actually going to have the ability to detect faces in it. So next, I need to arbitrate the connection to our session. So session.connect connects us to a video session, video call. Session.disconnect disconnects us from the session, and unpublish stops the publisher from publishing their video session. So this next step here is actually what's going to happen when the detect faces button is clicked. We're just going to tell all of our renderer elements to start detecting faces. And now this function here is actually what's going to happen when the stream created event callback is called. The stream created event is what happens when someone joins your conference. So like when a new video and audio stream is added to the conference. So for each video and audio stream, we're going to create a new renderer object. We're going to toggle its face detection so it's in line with the rest of the elements detection, face detection state. And then we're going to add that element to these renderers so it actually shows it on the screen, and we're going to subscribe to that incoming stream. Now, now that we have that layout and session initialization logic working, we need to manage the actual real-time face detection and displaying of our boxes. So by having our face detection video renderer implement iVideo renderer, which is that interface that I told you about earlier, we're going to get each frame that comes into each renderer. So for our publisher element, we're going to get each frame that we're publishing. And for each of our subscriber elements, we're going to be getting each frame that comes in from the subscriber. So all the video frames that are coming in are going to be coming into our individual renderer components. Then we're going to draw, we're going to intercept each frame. We're going to run face detection on it, and then we're going to draw a rectangle for each frame, or for each face that we detect in each frame. And finally, we're going to render the frame. So here's the beginning of the render frame function. The render frame function is called each time we get a new frame. We create a new writable bitmap, and that's what we're going to use to at the end of the day to do our face detection. And then we're also going to draw on that when the time comes. So essentially all we're doing here is we're creating the bitmap, setting the image source of our brush for our renderer to that video bitmap. That effectively means that we're going to draw on our canvas whatever the contents of the bitmap is. And then the next thing we need to do is we need to marshal the buffer from the frame into an OpenCV image. So if we're detecting since we're detecting faces, we're going to do just that. The image is constructed as a BGR byte image. So, and it's actually pulling in the frame's width, the frame's height, stride, and this is the actual buffer, the buffer that it's reading in from the unmanaged code into that image. And then it's actually going to scale the image down. So this reduced right here, image.resize. So that does it actually compresses the image into a smaller image so that our algorithm can run more quickly over it. If I did this if I ran this with a scale factor of 1, so just gave the same image, the detections took about 100 milliseconds. But if I scaled it back to a factor of a quarter, it ran in 5 to 10 milliseconds per frame. So I found it kind of important to scale each image down as it came in. Now, because we're actually doing stuff with the renderer, this all needs to run on the main thread. So we actually don't want to do the face detection on that thread. So we're going to push each image off onto a blocking collection that we have instantiated here, this images collection. And then this faces, which is just another field in our class, is actually going to contain all the images, all the faces that we detected. And so we're just going to draw the rectangles for each face that we detected onto our video bitmap, and then we're going to actually render the frame. So meanwhile, like I said, we don't want to run the face detection on the main thread because this is a WPF application. If you're running this all the time, you're locking up that main thread, so you want your user to still be able to use it. So this bit of code is actually going to be running in the background. Like I said before, this images collection right here is a blocking collection. So whenever I do a take on that, it's just going to wait for a new image to actually come into that images collection. Then we run our detect multiscale on the image, and that's it. That's all this function does. If we actually toggle off face detection this token will throw an operation canceled exception so that we can exit nicely out of this thread right here. So we're not occupying it. And this images collection is actually a concurrent stack. And the reason I use a stack and not a queue is because the most recent and most relevant images are always the same. So if for some reason the thing fell behind, you always want to get the most recent image. So now that we've detected faces, we're going to drop into this last function right here, which is actually going to draw the rectangles on the bitmap. Now we need to scale back up our coordinates in X and Y, that because we scaled them down before. And also a little bit of backstory here. The OpenCV rectangle function I showed you earlier doesn't play nicely with these bitmaps, so I needed to find another extension library to use for this. And which is really nice, but the really strange thing is the X's were all rendered in points, whereas the Y's were all rendered in pixels. So I needed to add a little bit of pixel point conversion logic right here to convert the pixels back to points for this thing to actually draw the X's correctly. It is really kind of odd, but it's fine. Regardless, this draws a nice blue line through blue lines through our image to actually display our rectangles. Hold on, let me just kind of show you this running in real time. I need to mute my camera real quick because Microsoft doesn't share cameras nicely between applications. So let me pull up. There it is.
We're not seeing anything yet.
Yeah, sorry, I haven't. I just had to find the things.
Okay, there you go.
So here we go. So now this is my solution with the face detection video renderer and the real-time face detection. So I turn it on, and what I didn't tell you is I have another video call running to my left on my work laptop. If I connect to, I pop in and I can see myself. That's my laptop. And if I click the detect faces button, you'll actually see it actually start to detect my face. And now I actually have the profile face detection set up here in this sample. So it's actually detecting my face and profile as well. But if I tilt my face like this, you'll see it actually go away. If I tilt it up, same thing. But yeah, so that's actually detecting in real time. And like I said, this was taking 5 to 10 milliseconds per frame. And when you're talking about video conferencing, usually you're at most looking at 30 frames per second under good circumstances when RTC is playing nicely. And what that works out to is you get a new frame every 33 milliseconds. So 5 to 10 milliseconds per detection is effectively real time. All right, so let me turn this off.
Whereas 100 milliseconds would not.
Exactly.
Yeah.
Which is exactly why I scaled that back to a quarter the size, because that really allowed it to run truly in real time. And it, like you saw, it ran on multiple video streams too.
Yeah. It seems odd though, doesn't it? To us, we're seeing, well, the bigger the image, the better it is, but it detects just fine on a much smaller one.
Yeah, like I told you before, the
bobbleheads will show up. Yeah.
Yeah,
if you take off the gloves. Yeah.
All right, let me find my. I have so many tabs. I have so many applications open all the time. It's hard for me to find my slides.
It's unfortunate your father got Roger Clemens in a Yankees uniform instead of a Red Sox.
I know.
That's another story. Yeah.
What are you, a Sox fan or something?
Yeah. I got a lot of family from Boston.
I actually think I hear it a little bit in your accent, but I could also be making that up.
I grew up in Connecticut, but my wife's from Boston. I lived there for many years. So
there we go. Yeah, so that was real-time face detection.
It's pretty cool.
For our last little bit, we're going to be covering some other pretty important concepts. I'm not going to get too deep into these, and I'm going to use a couple of really contrived examples here, but this is going to lead us to all sorts of really neat things. This is actually the lead-in for panoramas and also augmented reality. And that's feature detection, feature tracking, and image projection. So the first thing we need to really think about is what defines a good feature. And this is not something that's subjective. We need a concrete definition for our programs to understand what our program is going to be looking for. Then we're going to be using an orb detection method for detecting features in images. And next we'll be using the descriptors that we get from those features to match features between images. And this will eventually lead itself into image projection. So what's a good feature? So a good feature from our perspective, what we're looking at pieces of an image that we can correlate between two very similar images of very similar scenes. So we need like we need an objective definition of like what defines a good feature for this problem space. So a good feature is a section of an image that has multiple edges. Now, why is that? Well, think about it. If you're comparing two images to each other, and you're only looking at a very small portion of that image, if you don't have any edges at all, you've nowhere in that little neighborhood that you're looking at, there's no color changing, so you can't distinguish it from any other place in the image that has the same color. If you're looking along one edge, like we do here, you can't really distinguish that from any other place in the image that's on that same edge. But if you're looking at a part of the image that has multiple edges, like this, that all of a sudden becomes very distinguishable between multiple images. So effectively, when we're looking at when we're talking about features that we want to look at for in images, we're really talking about corners. And we're going to use these corners or features to correlate items between different images. So now this is a little bit of code here that actually does the feature detection on one image. So it generates this orb detector and calls detecting compute on it. Orb stands for oriented, fast, and rotated brief. Fast and brief it's a compound acronym. So fast and brief are their own acronyms, which I will get into, I won't expand upon. But this constructor right here tells it, all right, so this detector, every time we try to detect something, it's going to pull 10,000 most distinguished features in this image. And it's going to store those features in this vector right here. And yeah, we call it detecting compute, which actually detects all the features in the image. And then we use this nifty little features 2D toolbox that MGUCV has to draw all the key points on the image. So as you can see here, the features that are being highlighted here, those are where multiple edges in the image are coming together.
It looks like a kid went crazy with a crayon or map marker.
Well, the first time I gave this talk, I used red, which is very odd when you're looking at my eyes.
Yeah,
This looked like
right.
eyes.
You're like the devil, yeah.
But yeah, I decided to tone it back and use blue instead. So because we've detected these on places where edges are coming together in the image, we can really easily correlate them between forthcoming images. The next thing we're going to do, now that we've detected some features, is do a feature match. So we're going to use a k-nearest neighbors, KNN, matching function in the brute force matcher. Brute force matcher does just that. It goes through every feature and tries to brute force match it between every other feature that's detected in another image. So we add these descriptors that we got back here, we got from this detecting compute, and that describes each feature. We add that to our brute force matcher, and then we run a KNN match with the second set of descriptors, and we store the output in KNN matches. Now, k nearest neighbors is like it looks for the nearest neighbor that kind of makes sense, and it tries to and it looks for like a certain number of them at a certain distance. So the distance I'm using here is 400, and by matching these two and using this like arbitrarily set 400 distance, which is meaningless, I just found it to be useful for the sample that I was doing. You're actually able to find and create correlations between different features in an image. And here you go. So you see the green lines here that are drawn between the two images. Those are actually the matches that it found. Now, it does a pretty reasonably good job. You can see there's a lot of them. And the reason we want to use a lot of them is because the more we use, the more robust it is to outliers. Like this one and this one here are kind of outliers. They're pointing at like funky things in the image. They don't really make any sense. But yeah, the more features that we have detected, the more robust we are to these outliers. And that actually lends itself really kind of cleanly to our last topic, image projection. So if we want to project something onto another image, we need to we need to identify a region in that image that we want to project onto, but we need to keep track of that image as we're progressing through, over sequential frames of sequential frames of that image. So that's where we get into this last topic here. So to do multiple image projection over multiple frames of an image, we need to keep track of the features between the image and build a translation matrix called homography to map the old pixel locations onto the new ones. So the system of equations that this sets up, this is a linear algebra problem, has 8 degrees of freedom in it. So all that means for you is that in order to actually create one of these translation matrices, you need to have 4 matches between the 2 images. And that actually allows you to compute something called a homography. And that homography is what you use to project an image onto another. So think about what you can do with the 2-dimensional image. You can move it around, which is called a translation. You can scale it, increasing or decreasing or increasing the size. You can rotate it. You can perform what's called an affine warp, where you can do a change of perspective, where you change the way you're looking at something with your camera. Now, all of those different transformations can be generalized into this upper matrix right here. And you don't need to know this. It's a lot of math, but I just want to kind of highlight the level of simplification here. So this whole thing simplifies to this matrix, and that matrix is called a homography. And that homography is actually what's used to do the image projection. Now, this last bit of code here is just a toy example. So it takes a picture of a cat that I found on the internet and projection onto my face. So I run that same facial detection algorithm I showed you before over this to actually get the region that I'm going to project onto. And then I just use the 4 corners of that rectangle as the 4 correspondences I need between my 2 images so I can perform the projection. And then for the from our cat image, we just take the upper left corner, upper right corner, bottom left corner, bottom right corner as, again, the 4 points that we need to match. And then we can use this find homography function to find the homography between the source points, which are our cat image, and the destination points, what it's going to be projected onto. Then we can call this warp perspective function, and that actually changes the cat image to be in the same space as the image that we want to project onto. And then we can just copy that onto that space. And here it is. This is my face replaced with a cat face. It's a little bit crude, but you get the point. Now, if you wanted to project something onto a running video, you can do that as well. You would just need to keep track of the image space you want to project onto and update the homography that you're using for projection as you go through each frame of the image. I really hope that you enjoyed this little stroll down computer vision way. It's a huge field, and we've really only scratched the tip of the iceberg of what it can do. Before we go, I just want to tell you a little bit more about me. I've been a developer for about 7 years now. I'm a .NET developer naturally, And I'm the .NET developer advocate at Vonage. So I got my start working on the global positioning system, better known as GPS, and I also worked on the American and UK's air traffic control systems prior to moving into advocacy. And at night, I study computer perception and robotics at Georgia Tech. Go Yellow Jackets. You can follow me. You can follow my blog on Dev2. You can look at my blog on our Vonage blog, nexpo.com/blog. And you'll see there's a bit of a theme to my work. I tend to like to explore computer vision and artificial intelligence techniques and integrating them with .NET and Vonage's awesome set of APIs. You can follow me on Twitter. I'm at Lorello. And also, I'll just give a little bit of a shout out to my company, Vonage. We have a full suite of communication APIs, and there's a cute little jingle here that I like doing. I'm sorry, I just need to do that. It's too much fun.
Yeah.
But yeah, so Vonage has a full suite of communications APIs if you want to send an SMS message, WhatsApp, Facebook message, MMS. Obviously, if you want to do video conferencing, phone calls, we have all that kind of stuff. You can check out our developer documentation at our award-winning documentation website, developer.nexpo.com. We also have this coupon code here if you want to sign up for €10 worth of free credit. And if you want to learn more about our Vonage Video API, you can visit this link right here. So, wrapping up, here's some more resources. So everything I've showed you up to this point is available on GitHub. I found the MGUCV docs a little bit unhelpful as they're very high level and they really don't explain that much. But as I said, the OpenCV docs are really very useful. And if you're interested in computer vision, I definitely recommend giving them a read. So does anybody have any questions?
That was really great. You know, last time I looked at OpenCV, it was pretty daunting. I don't think I really ever looked at it as a .NET library.
Yeah, I hadn't either until I actually came to work at Vonage, and I'm like, oh, let me see if I can build a sample using the video API, because I saw that it had that on frame function. But yeah, it's pretty neat.
Yeah, cool.
I got a question right here. Have you used this kind of technology when it comes to verifying users for logging in?
You mean like, so you're talking about like, what's the thing that Apple has, the face unlock thing?
Well, same Windows 10 has it too. So
yeah, right. So that technique I showed you before is only appropriate for facial detection. You can use a similar model, but you need to actually build a convolutional neural network or have some other mechanism for doing that kind of biometric screening. Yeah, that does not generalize nicely to facial recognition.
Well, in my opinion, I think it's a good way to let people in, although it can't present itself as a problem. I mean, there are multiple people around the world who share the same facial features as anyone else does. Like,
right.
Like, what if there's someone else that has the same facial features as I have, and they can easily log into an application just by using their face?
I think I think Apple said that the robustness, I think there's a 1 in 10 million chance that someone's able to use their face to unlock your device, which actually is quite a bit better. I think it's magnitudinally better than their old thumbprint unlock thing, where I think 1 in 10,000 people would have a sufficient match to actually log in. But again, that's facial recognition, which is a different, completely different field of study from the facial detection thing that I showed you earlier.
The facial detection being a much simpler thing.
Oh yeah, it's a vastly simpler model to build. You just need to construct that model based off of those HAR-like features and just run a quick cascading filter over it. It's quick and dirty, not that hard to train, runs super low overhead. Yeah, it doesn't need that much. It's not that intense. when you get into like Azure, for example, has a Faces API, which I don't know if they might have just shut it down over some political concerns, or they might have just stopped the police from using it. I forgot which. But they have Azure Faces is the thing. There's actually a blog that a colleague of mine did where he actually used the Faces API, but he used it for sentiment analysis instead of actual recognition. But I think you can use it for recognition as well.
Okay. I think it really sounds cool. And I see that you posted a GitHub application that deals with facial detection.
Yep.
And that's implemented in C# or the .NET framework, right?
Yeah, C#. It's all.
Nice.
I think it's 4.5.2. I think is the framework that it's using. And it's that same sample I just showed you.
Coolness.
Yeah, I have to check that out.
Looking at it right now. But
GitHub, here we come.
Yeah. So to give you some perspective, so this second one here, WPF facial detection in OpenTalk community, that's like that full sample. That's the full runs facial detection in real time. This one down here, facial detection, is just like a little contrived example that just does it on one image. But if you want to see this running in real time, this second one here is what you want to look at.
Cool. Georgio Angelov, right?
What'd you say?
It's on your GitHub account, right? Giorgio Angelov?
Oh,
wait, no, that's probably-
S Lorello 89.
Yeah, let me go ahead and drop these in the chat.
That'd be good.
Yeah, that's a good idea. Here's one this is the WPF face detection one. That's the one that runs in real time in a WPF GUI.
Okay.
And yeah,
Okay, I got it. Thanks.
Yeah.
I'll just link you to my user page to my user too, and GitHub.
Yeah. I got the facial detection.
Awesome.
Excellent. Well, thanks a lot, Steve. I appreciate it.
Yeah.
Maybe it'll come back sometime in 6 months and give us some more.
Oh yeah, sure. Just let me know.
Yeah. Cool. All right. Anything else, anybody?
Just thanks, Dave. Thanks, Steve. This was interesting.
Yeah.
Cool.
Good. Glad you could come, Scott. All right.
I'll try and make them more often.
Yeah.
Tuesdays are rough for me sometimes.
Yeah.
Okay. Have a good night.
All right. Good night. I'm going to stop the recording now.
Yeah, thank you so much. All the best to everyone.